Alright, I'm on a roll with these doing exercises, so let's keep going. Let A be Noetherian and let fancy A be an ideal. I want to prove that there is some natural number n such that taking the radical of A and raising this ideal to the power of n will be contained in A. Now to prove this, when I was thinking of this, I was like, oh, Noetherianity. Oh, so we're going to have to want to use the chain condition, especially since we're looking at like Ra raised to an n and we're looking at n over the natural numbers, and I was like, okay, so yeah, let's try to find a chain. Nope, guess that's not how you do it. You want to use finitely generated condition. And I came up with this by asking a classmate. I have no idea how I would have come up with this. So anyways, since A is Noetherian, Ra is finitely generated, say it's generated by A1 through AM. So for each I, AI is contained in this radical ideal, meaning that raising it to some power, say Ni, will be an element of A. So then if we let n be the max of n1 through nm, then ai to the n will be an A, because what you can do is you can write ai to the n as ai to the ni times ai to the capital N minus, should be capital N, minus ni. And then the thing on the left will be an element of the ideal, or the thing on the left will be an element of the ideal fancy A, and the ideal on the element on the right will be an element of the overall ring. And since ideals are closed under multiplication by arbitrary elements of the ring, this product will be in this overall ideal. So that's that. So now I claim that taking this radical ideal and raising it to the power of n times m, where m is the number of generators of the radical ideal, and capital N is the max of these things. I claim that raising to this power will give you a subset of this ideal fancy A. So to prove this, take an element in here, which means that we can write it as a product from 1 through n times m of bi, where each bi is contained in R of A. And since R of A is generated by these elements A1 through AM, we can write each BI as a sum from 1 to M of CI, J, AJ, where the CIJs are coefficients in A. So A is equal to the product of sums of this form, which we can write out as this if we wanted to. So now, if you take an arbitrary element of this product here, then what are the terms going to look like? The terms are for each factor here, you're going to choose one of these terms. And then you're just going to keep going and choose one of these terms from every single factor. And then you're going to multiply those together, and those will give you one of the terms that's involved in the sum that defines A. So if you do that, how many things are you multiplying together? You're multiplying together, well, we go from 1 to capital N times M. So there's going to be N times M things that you're multiplying together to get this single term. And for each of these N times M things, you're going to have one of them will be like a CI, J, but the other one will be one of the AJs. And so you're choosing a particular A1 through AM for every single term in one of these factors, and you do this n times m times. And so by the pigeonhole principle, if you look at how many this product or this particular term could have, like, so from some of these factors, you'll choose the one associated with A1. From some of them, you'll choose them associated with AM. And maybe you won't choose any of the ones associated with like a sub m minus 1, but whatever. If you look at, if you combine all these things together, then you'll have a bunch of the C's multiplied together, but then you'll have each A1 to some power times A2 to some power times A3 to some power times blah 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 blah. Some of those powers might be 0, but since we're taking one term from each of these factors, and since there are n times m total factors, the sum of the exponents of the AIs must be n times m. And since there are only m of them, at least one of the AIs must have an exponent which is greater than or equal to n. So then this particular AI to the capital N will be an element in fancy A. And then you're just taking an element in fancy A and multiplying it by a whole bunch of other stuff, which will keep you an A. And so this particular term of the sum will be contained in fancy A. And this holds for every single term in this sum. And so therefore, this product here, you can write it as a sum of a number of like finitely many things which are contained in this ideal fancy A. And therefore, that gives you an element of the ideal. And so A is in fact contained in, it's an element of this ideal fancy A. And this holds for every single A in this radical raised to this power, and so this is contained in here. So really what you end up using here is that that in Noetherian rings, ideals are finitely generated, and then you use the pigeonhole principle. Although I have no idea how you would come up with that.